Happy day! In today's session, we will see what is a minimum spanning tree. Before going into minimum spanning tree, we have to know what are tree graphs, what is a spanning tree, and then what is a minimum spanning tree. In order to construct a minimum spanning tree, we will see certain algorithms along with examples. Tree graph. A graph T is called a tree if T is connected and has no cycles. Consider figure 1. In figure 1, we have 9 vertices and 8 edges, and figure 2 has 13 vertices and 12 edges. In both the figures, there are no cycles and each figure is a connected one. Since there are no cycles, we call it as a tree. Also, consider the first figure wherein in a tree there is only one simple path between any two vertices. Here in this figure, if we have to add any edge to the existing vertices, it will form a cycle and no longer it will be a tree. For example, if I connect V1 and V4, it will form a cycle, that is V1, V4 and V2 will form a cycle and no longer it will be a tree. Similarly, if I delete any edge from the existing tree, then it will become disconnected and it will no longer be a tree. So, moving to spanning tree. A subgraph T of a connected graph G is called a spanning tree of G if T is a tree and T includes all the vertices. That is, the definition of tree will hold good along with an added point that it has to include all the vertices of the graph. So then you call it as a spanning tree. Consider the figure that is displayed there, that is G, which is a graph. Now T1, T2, T3 are the spanning trees. For example, if you take T1, all the vertices of the graph G are present there and no cycles exist. Also, it is connected. Similarly, it is the same for T2 and T3. If you have such figures, then you call them as spanning tree. Then, G is a connected weighted graph. In case, so long we just saw a graph without any weights. Now, in case if you have a graph with weights, weights are nothing but non-negative numbers allocated to each edge is a weight. So, if you have a weighted graph, then after constructing the spanning tree, add up all the weights to arrive at the weight of the edges and the spanning tree is obtained. Now, moving on to minimum spanning trees. A minimum spanning tree of G is a spanning tree whose total weight is as small as possible. That is, we can construct many spanning trees from a given graph, and for each spanning tree, if we calculate the total weight, whichever weight happens to be a least weight, then you call it as a minimum spanning tree. So, in order to do that, we use certain algorithms, and here we use Kruskal's and Prim's algorithm for the construction of minimum spanning tree. Kruskal's algorithm, the input is a connected weighted graph G with n vertices. Output, minimum spanning tree MST. Algorithm. Step 1. Arrange the edges of G in the order of increasing weights. Step 2. Start only with the vertices of G and proceed sequentially. Add each edge which does not result in a cycle until n-1 edges are added, and then exit. So this is the algorithm wherein for any given weighted graph, we consider each edge and check for the weights, arrange them in the increasing order, add each edge whichever satisfies all the rules of the spanning tree. And then we have to continue the procedure until n-1 edges are added. So for example, we can consider a problem wherein find a minimum spanning tree for the following weighted graph using Kruskal's algorithm. Here, this graph has 6 vertices and 9 edges, and each edge has a weight. So now each edge has to be ordered by the increasing weights. First, BD has the least weight 3, followed by AE, DF and which has 4, but there is a tie between AE and DF. So here we can consider the alphabetical order. So it is AE and DF, followed by BF which is 5, CE 6, AC and AF, BE are again 7, 7, 7 each, and BC is 8. So now all the edges have been arranged in the increasing weight. After arranging them, we have to check if it satisfies the condition to add to the spanning tree. So BD has weight 3, yes, it has to be added. Similarly, AE has to be added, DF has to be added, but BF will not be added because if we add BE, it will form a cycle. And CE is again added, AC is not added as it forms a cycle, and AF is added, after which BE and CE are not added because they also form a cycle. So thus the minimum spanning tree which is obtained contains only 5 edges. Weights of each edge of the spanning tree is added and it results in the weight 24. Then Prim's algorithm. Again, the input is a connected weighted graph G with n vertices. Output is the minimum spanning tree. Step 1. Start with an arbitrary vertex and add it to the minimum spanning tree. Step 2. Examine all edges connected to the vertices already in the minimum spanning tree and select the one with the lowest weight that leads to a vertex not yet included in the tree. Step 3. Add the selected vertex and its connecting edge to the minimum spanning tree. Step 4. Repeat step 2 and 3 until all vertices are included in the minimum spanning tree. So now we shall apply this algorithm to a problem to see how a minimum spanning tree can be constructed from a given graph using Prim's algorithm. So here again we have the vertices and the edges which have weights. So now when you take the first step, we can choose a vertex arbitrarily and we have to check all the edges from that particular vertex and then select the edge with the least weight. So here 1 and 6 has the least weight. Then moving on to the vertex 6. In vertex 6 you have 6 to 5, which means there is only one edge and the weight is 25, so it is included. Now consider the edge 5, but 5 has 5 to 7 and 5 to 4, that is 24 and 22. Minimum is 22, we include 5 to 4 with the weight 22. Then consider 4 again. So when 4 is considered, we have 4 to 7 and 4 to 3. Minimum happens to be 12. So 4 to 3 is added to the minimum spanning tree. Then consider the vertex 3. In 3, you have only one edge 3 to 2, which is 16. So 3 to 2 is added with the weight 16. And then consider the vertex 2. The vertex 2 has 2 to 7 and 2 to 1. The minimum weight is 14. So 2 to 7 is added, and now all the vertices of the graph have been included. So we can stop the procedure and find the total cost, which sums up to 99. So this is how we obtain a minimum spanning tree using the Prim's algorithm. To sum up, we saw what is a tree, what is a spanning tree, and then the minimum spanning tree, and also the two algorithms to construct the minimum spanning tree. Thank you.